Hello everyone, it's June 26th, another late night, mainly because I worked a little bit more today at night and noticed that whatever that I implemented a few days ago was not working. Pretty bad. Pretty bad. So yeah, I need to think hard about it tomorrow, how to deal with this. Dev complete is over. So, or maybe I have only one day too. I mean, I think the changes can be made in one day. That's what I believe. But boy, this is going to be a stretch. All right, given the root of a binary search tree, return a balanced binary search tree with the same node values. If there is more than one answer, return any of them. Balance a binary search tree. Same node value if there is more than one, return any of them. Binary search tree is balanced if the depth of two subtrees of every node never differs by more than one. Okay, I remember there is an algorithm, but I don't remember how. Isn't this just like rebalancing, right? It's a good piece of code algorithm to know. How do we rebalance it? Honestly, I do not know. We start with a binary search tree, and then we need to rebalance it by some sort of recursion. No, maybe. How? So you're given a tree, right? Each subtree, so the left height and the right height must not differ by more than one. So you got the left height and the right height. Okay, then you go into the right. You will do left height and a right height, and you go right at the end. So 3, 4, right? That 3, 4 is good. And then we return 2, and then we have 2. 2, the left is 0, and the right, the level is 2. So that's bad. So we need to rebalance it. How do you rebalance it? You can put 2 here. Right, move this down. So basically we say if we have a root, and then the left, the right, if one side is larger than the other, then we will pull it down. But if you pull it down, it is still a binary search tree. So left is everything smaller, right is everything bigger, right? So if I want to rebalance, right, let's say we have a root, and we have everything on the left, we have everything on the right. So it's not balanced, we need to rebalance. How do we rebalance this? Because this is smaller, so we have the root here, right? So this is smaller, so I can elevate this, right? Let's do like this. So I can elevate this. So this has a whatever, and this has a whatever. So if I elevate this, okay, so this one comes to the top. now I have this part, I have the original this subtree, and I have this subtree, right? Then I need to balance, I need to handle these two, or I handle this subtree and this subtree. How do I merge these two subtrees? Well, I think it depends, right? It depends. Because these are smaller than this. These are smaller than this as well. But these are bigger than this, right? So this I can say delink this, put a link here, right? I can put a link here. And then on this side, I added one level, right? On this side, I added one level. On that side, it's the same. So if these two are the same, then this will work. If this is bigger than this, it'll work. What if this side is bigger and this side is smaller? Yeah, what if this one is bigger, this one is smaller? Now in that case, when we want to merge, because yeah, we added this one. Yeah, what if the left subtree is bigger than the right subtree? Or we prevent that from happening. If we have a bigger left than a right, even by just one, I will rebalance it. Right? I will rebalance it by shifting this one up. So we always want to make it a left is equal to or one smaller than the right. Yeah, because there are two scenarios, right? If it's balanced, that's good. If it's not, if it's balanced in such a way that left is one smaller than the right, is good. If left is one bigger than the right, then we have this node. So we'll elevate this node to the top, right? So we elevate this node again. We elevate this node to the top. So this node has a left, has a right, and now we have a this, now we have a this. Right? So this node go to the top, and we reduce one level on here. So we have this, because we know this is one bigger than this. So now this side is the same as this side, right? So what we do is we put this one here. Yeah, because this is one bigger than the other. What if we have this side is a lot bigger? Yeah, what if it's a lot bigger? Like what you're dealing with is you're just manipulating this. So when you do this move, go up, do this, right? You'll go up and do this, and how do you know that it's enough? Yeah, how do you know it's enough? Right, one side if it's a lot bigger than the other side. You do 1. Yeah, what if it's too bigger on one side? Well, if it's too bigger on one side, do you do 2? Well, you do 1, and you do another one. You move that many times. Okay, let me think. Yeah, so each subtree is guaranteed to be even or slightly biased towards the right. Okay, that's the guarantee. Or slightly biased to the left. I guess it doesn't matter. One subtree is longer. Well, but I mean, we work from the bottom, right? So everything is balanced. Okay, everything is balanced. The left-hand side is balanced. The right-hand side is also balanced when we are kind of merging this. So whichever side has more layers, then we will move it onto the other side. Move it onto the other side, and then we are sure that these are balanced, right? We're sure that these two are balanced. So when we make this move, and how do you guarantee this and this are balanced? All we can say is this and this is unbalanced, right? The left subtree is not balanced with the right subtree, and the right subtree is too big. And I say I'll move one side up, and I move this one. This can be the really long one. Actually, it's not going to be a long one. It's just going to be almost one bigger than this, right? If this is the long one, then I move it here. Yeah, then it will be wrong, right? Because this will be, if this is 1 bigger than this side, or 1 plus 1, it will be 2 bigger than this side. But hold a second. I may not need to I can just reconstruct it, right? Yeah, I think I can just reconstruct it. I don't think I need to update this. Although updating this probably is the right solution, but for this one, I can just reconstruct it. Right? Because I can traverse this, I get a list, and then I just pick the middle, and then we pick left and we pick right to make. Okay, so yeah, that will work. That will work. But it's not what we want. Right? I can see we have to check the answer and then read the good solution. But for now, for the solving this problem purpose, I think we'll just cop out using the simple solution. Just rebuild it. It's basically what I want to do. We'll just rebuild it. There's no point. Alright, so rebuild it. What we're gonna do is we need to traverse it first to get the list. So we need to say list of integer. Right, that's unique, right? Hopefully. Yeah, I think it will be unique. So will be this list, new array list. Okay. And then we'll have private void traverse. Okay, so we need a node and we need a list. Alright, so basically we need to do a left root right traversal. Right. So we say if node is equal to null, we'll just return. Otherwise, we'll do traverse node.left list, and then list.add node.val, and then traverse node.right. Right. So we go left all the way down, get its value. Then we go to the right. So this will help us populate. Right, so we populate it. Now we're gonna do a new one. We call it private void create balanced BST. All right. Then we need how you propose to do this. So let's say we have the list, right? We need a low and a high. Yeah, we need low and high. We need a list, low and a high, and this one. Okay, so we have the list integer list. Okay, int low, int high. Right, we have a low and high, and this one shall return. I think this one shall return a tree node. Okay. All right. So if low is equal to high, right? So if low is equal to high, then we return new tree node. Just need a value. Value is going to be list.get low. Okay. Otherwise, then we say mid equal to low plus high divided by 2, right? So we do a mid. We say return new tree node value list.get mid. Okay, left, so will be create value as tree list. Low doesn't change. High shall be mid -1. Right, mid -1, so we get a mid, so we have mid -1. So what if low and high are differ by only 1? So mid will become actually low. So yeah, so basically if low is smaller than high, no, low is larger than high, should return null. Right. That's the left hand side, and create list this should be mid plus 1. And I'll just return create list 0 high will be list dot size minus 1. Okay, let's give this a shot. Yep, so this will work, but I consider this a little bit cheating. Alright, this is not the right solution because we are not rearranging the original tree. Instead, this solution feels like a cheat, right? We obtain the list. Yeah, we obtain the list form. Obtain the sorted list, right? Sorted values of the original BSD, and then recreate a new one. A new one that is balanced. ON. So traverse is ON. Create the tree. Yeah, I think create a tree is also ON. Because you have to do every node. Alright, let's hope this is right. I mean, maybe we can do, some check. That's a good check. Yeah, it works, right? It works, but I don't like it. Which means it's time for the solution. There gotta be a better solution. Okay, so this is what we did. All right, let's see. The rotating method. Day-Stout-Warren algorithm, the DSW algorithm. In-place method for balancing binary search tree. Rotations, which are fundamental operations. I actually was trying to do some rotation. Well, we'll see how they do. Right rotation, left rotation. Okay, let's just see. So we rotate. Wait a second. Yeah, that's what I said, right? You rotate here and you put the 4 here. Final line. Wait a second, what are you doing? No, you keep rotating right until you become a right skewered tree. Okay, I actually know about the rotation. It's like this, right? You rotate, and then you will, after you rotate, you need to, because after you rotate, 3 becomes the top, and then you have to append this 4 into 5. And this is actually not right because it's supposed to be 4. And you rotate here, you put the 4 there. So yeah, and I know the rotation. Count the nodes. And then we'll balance the vine. The left rotations. The largest power of 2 less than this minus 1. This calculation is significant as it identifies the largest complete subtree that can be fully balanced. The largest power of 2 that is less than n plus 1. Minus 1, so m equals to 3. Perform n minus m left rotations to partially balance the tree. This ensures that the remaining nodes will form a complete binary tree after the first set of rotations. Alright, let's see. So I move this here. We do another move. Wait, hold a second. Huh? What is this? I don't understand. So it said we first do left rotations. Hold on, I probably need to draw it. So we do this with 2, 3, 4, 5, 7. I want to do another one because so I do another one. We'll left rotate 3. Alright, we left rotate 3. So but we don't do anything. 3, 4, 5, 7. This is actually good already. And then we loop m is halved repeatedly. For each iteration, perform left rotation to balance the next level of the tree. I don't understand. This is it rotates on 4. Yeah, these are step I don't understand. Hey, what do you mean by... Hmm. I don't know. All right, I actually don't understand. I think I need some help. I think this is the algorithm in place tree balancing. All right, do we have... All right, we might have a video for this. All right, so I think that's it. That's it for now. I need to study this.